to your part 2 video for 6-1 key features of exponential functions. So this one we're going to look at some modeling. So we have that the population of some large city is about 4.6 million in the year 2010, and it grew at a rate of 1.3% for the next 4 years. It says what exponential function models the population of the city over that 4-year period. So let's look at a table. So I am going to make 2 different columns. T is going to represent my time. P is going to represent my population. So your time is going to be years since 2010. So year 0 is the year 2010. And of course, P is going to be in millions. So we're just going to say it's in millions. We're not actually going to write it out with all the different zeros to make it an actual million. So if I'm looking at the first year since 2010, so this would be 2011, I have my initial population. It grew at a rate of 1.3%. So I have to find 1.3% of 4.6 and add those together. Now, rules of exponents, or rather not rules of exponents, but both of these terms have a 4.6 in them. So I can actually factor that 4.6 out, and I'm left with 1 plus 0.013. Well, I can add those together, so that's 4.6 times 1.013. Now, if I look at 2, that's 4.6 plus, I have 13% of my total population. So it's going to be 13% or 1.3% of what I had previously. Well, what I had previously was 4.6 times 1.013, and so I'm multiplying that. I need to both have that number and add it back on. So I'm going to be multiplying by an additional 1.013. So let me, because I'm not going to be doing that 1 again. Let's rewrite that in a better way. So I'm multiplying that by an additional 1.013, which means I have 2 1.013s. Now I have 3 years. So I'm multiplying by another 1.013. Because you're always taking the previous value and multiplying it, figuring out what that 1.3% is, and then adding it back on. So that's where you get the 1.013. And so that's going to be 4.6 times 1.013 to the 3rd power. And of course, this 4th one is going to be the same thing, but this time it is to the 4th power. So our model here, and it looks like I need to erase some of this. Our model is going to be 4.6 times 1.013 to the t power, where t is years since 2010. Now, as we go through and do the second one, let me get some of this erased down here and see if we got all of this. Okay, so part B says, if your population continues to grow at the same rate, what's going to be the population in 2040? Well, 2040 is 30 years since 2010. So what we're really finding is P of 30. So that's going to be 4.6 times 1.013 to the 30th power. and that's going to equal about 6.78 million. So if this city continues to grow at the exponential growth that they assume, we can expect it to have a population of 6.8 million in the year 2040. So this introduces the concept of exponential growth and decay. What we previously had was a growth function, and that's because a rate was being added to 1. If you have a decay function, then you're going to be subtracting that from 1 because you have less and less of whatever your original amount was as the time goes on. Your growth or decay factor is going to be your B value. Notice for the growth, B is 1 plus R. That's how we got that 1.013 in the previous question. Your decay factor is 1 minus R. So that would be like if something decreases by 15%, then your value is going to be 85% of the original. So this brings us to example 4. We have a car that was purchased for $24,000. Our function, y equals 24 times 0.8x, can be used to model the value of the car in thousands x years after it was purchased. So first we want to know, does this function represent growth or decay? Well, if we look at the growth or decay factor, that's 0.8. So it's always going to be worth 0.8 of what it was the year before. Well, that's going to make your value smaller because, for example, if your car is worth $100, which I know there's no cars worth $100 unless they're really junk, but if it was worth $100, well, 80% of 100 is 80. And then the next year is worth 80% of that. Well, 80% of 80 is going to be 64. And it's going to keep going down and down and down. So because it is growing down, this is going to represent exponential decay. And I think I'm going to have to, well, I guess I'm not going to have to raise. Oh, the rate of decay for this function is 0.8. So since it's 0.8, that is 0.2 away from our whole number of 1. If it was 1, that means that it's retaining whatever value it's at. So we are losing 20% of value each year. And then it asks us to graph the function over a reasonable domain, and what do the y-intercept and asymptote represent? So to give this a good model of what's going on, I'm going to do my y-axis is going to be the value in thousands of the car. X-axis is going to represent years. So I have 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. Let's do 5, 10, 15, 20, 25, 30. So it starts off, I just jumped there. Year 0, my car is worth $24,000, so that's going to be right here. If I graph this, which you will want to have a calculator to go through and get some approximate values. So 24 times 28 to be, we do to the second power. So after 2 years, it's going to be worth, well, I guess I should start with 1 year. After 1 year, if you take 80% of 24,000, that puts you down at 19,200. So we're going to be right about there. And then after an additional year, it's 15,360. We're just above the 15,000 mark there. And then if we do the same thing 3 years, that's 12,288. So we're down to there. 4 years is going to be 9,830. So we're down here. 5 years is going to be 7,864. So we're about right there. 6 years, and I'm going all the way up to figure out where I'm at this $5,000 mark. So 6 years, I'm at 6,291. So 6,291. 7 years, that's going to put me at 5,033. So it's pretty much right on this line. So you can see it's going about right like that. So what's the y-intercept? The y-intercept here is going to be starting value of your car, so how much it was worth to begin with. The asymptote is going to be your lowest possible value. So eventually it's going to bottom out and be worth nothing, although you notice it decreases very quickly at the beginning and then it does kind of flatten. So each year it's losing less and less and less, but it is still losing money. And for the value of the car to get to be $5,000, so at year 7. So about year 7, that's where we're going to get that value of $5,000. So keep in mind, you spent $24,000 on this car, and after 7 years, it's worth less than a fourth of what you paid for it. So that's the way it goes with cars. They don't always hold their value the best. So this brings us to our last example, and we're going to talk about this. I'm going to go through some of the math for this. We have a museum that purchased a painting and a sculpture in the same year. Their changing values are modeled here. Notice both of these are increasing. You can see the sculpture, we have an equation here. Its growth factor is 7.5%. This one, we don't actually know the growth factor because it just gives us the equation, but we can see that it is going up, so it is growing. We could calculate the growth factor for that, but I'm not going to worry about that at the moment. It says find the average rate of change for the value of each artwork and which one is increasing more quickly. So which one is going to have an average rate of change that is faster. So for both of these, I'm considering f of 5 minus f of 0, and the whole thing is going to be divided by 5 minus 0. So average rate of change, let's see here, average rate of change, remember that's simply slope. So for the sculpture, remember my equation is the 50 times 1.075 to the x power. So that is going to be 50 times 1.075 to the 5th power minus 50 times 1.075 to the 0 power, all over 5 minus 0. And that gives me about 4.356 for the painting, which, by the way, I really enjoy the fact that the painting is of a graph. I could just imagine having a gallery full of artwork and all of it is math graphs and everything like that. That seems pretty great. My f of 5 is going to be 64.4. My f of 0 is 40. That's why they give you the ordered pairs there. And then that's divided by, again, 5 minus 0, which is just 5. So whenever I do that math, I'm going to get 4.88. So based on this, the painting is increasing. It has an average rate of change of 4.88. The sculpture only has an average rate of change of 4.356, which means that the painting is going to be increasing in value quicker than the sculpture. So if we had to guess at its rate, its growth factor, it's going to be greater than that 7.5% because it is increasing quicker. So that's your lesson on 6.1 on exponentials. These do come up periodically, and I know we're getting to this towards the end of the year, but it doesn't mean that it's any less important than any of the other stuff we've gone over. So please make sure you go back through, rewatch either this video or the previous video, and contact me if you have any questions on exponentials.